All right, so today we're going to look at our last section on transformations that we haven't studied yet, and that's a translation. Okay, so we did reflections, we did rotations, and now we'll look at the translations. Okay, so a translation, here's our definition. Okay, it's a transformation that maps every 2 points, P and Q. So what we'll do, we'll look at it as just a segment. Rather than trying to look at it as something really complicated, let's just simplify it and look at 2 points, okay, that make a segment. So every 2 points, P and Q, move to these points, P prime and Q prime, such that the following will always be true. The distance from P to P prime and Q to Q prime is the same. Okay? That's important. Okay, and the second thing, the segment from P to P prime is parallel to the segment from Q to Q prime. They're parallel. Or the segments are collinear. Okay, that's an or. It can't be both in statement 2. One or the other happens. Either the segments P prime, Q prime are parallel, or they're collinear. Okay, so there's an example of a translation. Okay, let's look at each of those statements and see kind of what that means in terms of the picture. All right, so I'm saying that the distance from P to P prime and the distance from Q to Q prime is exactly the same. And I just measured it. It is. What would happen if it wasn't?
It wouldn't look right.
What's the only way that could happen?
If you screwed up.
Okay, how? Let's say the distance between P and P prime was different than the distance between Q and Q prime. What would have to happen to your image for that to happen?
Rotation.
Well, it could be another transformation. It could be a rotation.
It could either be longer or shorter.
Yeah, or it could mean that you moved part of your object, but not the other part. It's like you stretched it. Okay? So if you did something like this, okay, in that case, maybe you stretched it out a little bit and rotated it. So now the distance between P and P prime and Q prime isn't the same. Okay? But with a translation, if you're moving the whole object together the same amount, every single point on the image is exactly the same distance from the corresponding point on the pre-image. Okay, and then statement 2. Which case do I have here? Is P prime and Q prime parallel or collinear? Which case do I have?
Parallel.
Yeah, it's parallel in this case. Okay, it's parallel. The only way it could be collinear is if you translated it from here on a line like that. Okay. Now in that case, P prime, Q prime, they would be collinear. Okay, and like our other transformations, a rotation is an isometry. Okay, meaning once you perform it, it doesn't change the length, doesn't change areas, doesn't change perimeters. It's an isometry. Okay, any questions on these 2 statements? Because we're going to do a proof today. Okay, and we'll have to keep kind of these ideas in mind. All right. Okay, we're going to prove the part of Theorem 7.4 that says using the parallel. Okay? This is the case where I've slid something and P prime is parallel to Q prime.
So it's always going to be parallel?
No, what else could it be besides parallel?
Collinear.
Yeah, it could be collinear if you translated it from here like that. Okay, if you translated it on a line like that. Okay, for this, I think we'll just write it out. Okay, rather than doing the statements and the reasons, let's just write out what we've got. Okay, what should we start out with? First thing. Yeah? Yeah, let's start out with what we're given. Okay, so we are given, and write down. PP prime equals QQ prime. And I've marked that, okay, in the diagram. And PP prime segment is equal to segment QQ prime, parallel, sorry, it's parallel. Okay, and I've also marked that in the diagram, okay, using the arrows. So they want us to prove that PQ is the same length as P prime Q prime. Basically proving that once you translated it, it didn't change length. Okay, what shape is that? Based on what you're given. You have a pair of opposite sides that are parallel and congruent.
Parallelogram.
Yeah, that's one of the theorems you can use to prove that this shape is a parallelogram. So P prime, Q, Q. Just naming the vertices going around, is a parallelogram. Anybody remember what theorem that was? In chapter 6? Let's see. That was proving shapes are parallelograms. I think that was in section 6.3. It's theorem 6.10. Okay, so if you want to look up why it's a parallelogram, that's the theorem. Theorem 6.10. Okay, what does that tell us? If that shape is a parallelogram, what else do we know? Yeah.
Opposite sides are congruent.
Yeah, in a parallelogram, opposite sides are congruent. So, PQ, segment PQ, is exactly the same as segment P prime Q prime, because opposite sides are congruent in a parallelogram. And that's basically it. So you showed that the shape you have here is a parallelogram. Opposite sides have to be the same length, and that's why translation is an isometry. Now this doesn't prove the case where if you took and slid it like this. Okay, if you do it like that, you don't have a parallelogram there, so you can't prove it the same way. But this at least proves the case when they're parallel. Okay, any question on that? Another idea. All right. Okay, so you might see the word in the book glide. Did you see like a glide? A glide is another word for translation. But there's another way we can do a translation. Right? We talked about something like this yesterday, okay, similar, when you do a double reflection. Okay, when we did 2 reflections back to back yesterday, what was special about the lines that we reflected over? So, and I had an example on the board, like line L1, line L2. What was special about L1 and L2? It doesn't always have to happen with lines, but it did yesterday.
They were parallel?
No, they weren't parallel. They intersected. Remember, they made an angle of, we called it X degrees. And when we did the reflection by another reflection, it was like a rotation of 2x. Well, today we're going to do 2 reflections again, but we're going to do it over parallel lines. Okay, so the 2 lines we reflect over, they are not going to cross. What do you think is going to happen here? If you've got 2 parallel lines, and you do a reflection and another reflection, what do you think that'll be the same as? It's not going to be the same as a rotation. That was yesterday. Kira, do you have any guess? So there's only 3 choices, and it's not a rotation. Well, we're going to do 2 reflections, and that's going to be the same as something else. So only one choice left.
Translation.
It's a translation. Right? It's a translation. Okay, so if you got 2 parallel lines and you reflect over both, it's the same as translating. Okay, so I'm going to show you a diagram. The diagram is going to have P double prime. That'll be the final point after reflecting twice, and P will be the starting point. Okay, then the following 2 things are true. If you draw a segment, which I'll do in a second, between the point you started with and the point that was reflected twice, it'll always be perpendicular to both lines of reflection. Okay, so if you draw a segment between your starting point and your ending point, it'll be perpendicular to both lines of reflection. And we get kind of an idea we had yesterday, this doubling of something. The distance between the point you started with and where it ended up at is going to be equal to 2d, where d is the distance between the parallel lines you're reflecting over. All right, let's look at a picture. Okay, so I have 2 lines, call it L1 and L2. And the distance between L1 and L2 is d. So if you take point P, reflect it over L1, becomes P prime, and then take P prime and reflect it over L2, becomes P double prime. Well, the distance between P and P double prime is 2d. Take the distance between L1 and L2 and double it. And that's also true for Q. Take Q and reflect it once, you get Q prime. Reflect it again, you get Q double prime. The distance between Q and Q double prime is 2d. And also, if I draw in a segment connecting Q to Q double prime, it's perpendicular to both lines of reflection. Okay, so it's kind of a special thing that happens when you do a double reflection over parallel lines. What happens if you reflect over lines that cross? kind of, you reflect twice, that ends up being, that's a rotation. How much would the rotation be in this case? Yep, x times 2, whatever x is. Good. Okay, so two different cases. All right, so I want you to look at that diagram. Okay, and in that diagram, we've got two lines we're reflecting over. Line K, line M. Okay, K and M are parallel. They don't cross. Okay, so when you take GH, okay, that's in blue, that's the original, and reflect it over line K, you get the line in red. G prime, H prime. And then when you reflect the line in red over line M, you get the one in green. G double prime, H double prime. Okay, and they give us a couple distances. They tell us the distance from H to B is 5 units. And the distance from D to H double prime is 2 units.
Was there any problem to solve there?
There will be in a sec, yeah. Okay, so they're just setting everything up. Okay, and I've labeled these two numbers in the picture. Distance from H to B, distance from D to H double prime is 2. All right, so I want to name some segments in that picture that are congruent. Okay, Dakota, could you give me a segment in that picture and then name a segment that it's congruent to? Okay, B what?
BD.
BD, all right. And what is that congruent to?
AC.
Sure. BD and AC. If those distances weren't congruent, K and M wouldn't be parallel. Yep. Okay, somebody else name two other segments that are congruent. Yeah.
Line HB and line CG.
H, go ahead, one more time. H,
B, CG.
HB.
HB.
Oh, HB, gotcha.
And double prime CG. C.
C is in a cat.
C.
C is in a cat, and G is in
C.
Yeah, isn't that C right there?
C double prime.
Yep, C's down at the bottom.
Yeah, double prime G.
Double prime,
G double prime.
G double prime.
Why did you say that?
Okay, so that one's a little more complicated to prove why that's true. Does everybody agree?
It's true.
Why is that true? Okay, let me give you another fact. I think that's a little easier one to understand with HB. HB is congruent to H prime B. That's a reflection. H and H prime are the same distance from the line of reflection. Okay, so you could say that. You could also say, well, so all kinds of other things you could say, but how would you arrive at this fact?
I think Connor has the answer.
And what I'm looking for is maybe some more congruent statements that if this is congruent to this, and that's congruent to that, and that's congruent to something else, then we could finally say something like this. So we need a couple more congruent statements. Yep, so what would be another congruent statement?
GC, G prime, C.
Okay, G prime C. All right, so he's talking about that segment. Yep.
And HB.
And, okay, I'm not sure how you got that one.
Or BH prime.
Okay.
Or H prime
Let me
B.
mark some. That's the same as that. You could say this segment is the same as that segment. This segment up here is the same as that segment.
So then A and then G prime and A and G are the same.
Yeah, I'm going to go back to Marquise. Can you tell me how you figured that out?
I don't know.
Because that's not an easy one.
Well,
To
what
figure
I
out.
was saying was HB and H prime B, and then you're going to take H prime B and you're going to take G prime C.
H prime, I got to write this down. H prime
B
B. Okay, yeah, we got that one.
and G prime C.
All right, let's check that out. H prime B, that's
I see what you mean.
this part. And G prime C, that's this part. You're saying those are the same?
Yeah.
Yeah,
So that means if you would have both written.
I think those are the same. So now, and then if this is the same as that, and this is the same as that, basically we just figured it out. That segment's the same as that segment. That segment on the top is the same as this one on the bottom, and that's the same as that. So there's all kinds of congruent segments here. It gets kind of complicated, but I think we've shown it. Okay. We might have already answered this question, but does AC equal BD? I think, yeah, we already answered it up in part A. AC is congruent to BD, so their measures are equal. Okay. The answer is yes. Okay. Let's look at it. So AC, right there.
That's not AC. That's G prime.
I'm sorry, yeah. AC and BD. Those have to be the same length, otherwise lines K and M wouldn't be parallel. Okay, so we already said that. Yes, because lines K and M are parallel. And the last thing is I want to know the length of G double prime. Let's go back up. From G to G double prime. So it's basically the length of that entire bottom side.
14.
Well, we don't have any numbers on the bottom side, but yeah, where do we have numbers?
On the top.
On the top. And this is a parallelogram, so we know the top side and bottom side are what?
Same.
They're the same. So if we can find the length of H double prime, it's the same as G double prime. So how'd you get 14? We only have a 5 and a 2.
Well, since A, HB, and
HB?
H prime B is
Yep.
congruent, so it's 5.
Yeah. B to H is 5. H prime to B is also 5. And
H double prime to P, or the to B, H double prime to B is 2, so H prime to D is 2.
yeah, I'm just going to do it in a different color. If this part is 2, then this part is also 2. Okay? And then if this part is 5, it forces that part to be 5. So we have 5 and 5 is 10. 2 and 2 is 14. And if the top side is 14, so is the bottom. And that's it. Right, so any questions on that? There's all kinds of congruent segments there. We named a few. So sometimes when we describe a translation, we use coordinate notation, like that. So we write down the point xy, put an arrow, and then we put A and B are the amounts that it's shifting by. Okay? A and B are the amounts it's shifting by. A can be positive or negative, and B can be positive or negative. So if you wanted to say, all right, take all your points and shift them up to left 3. The way you could write that is up and down. That's your y value. So put a +2 on them. Left 3, that's your x value, and left is negative. So -3. So this is one way to describe a translation. Okay, x -3, comma y +2. Any question on that? All right, so if I gave you an example, which I'll do next, like this, x comma y, who can describe what does this transformation say to do?
Down 3 on the x-axis.
Can you say that again?
Down 3 on the y-axis and
No.
on the x.
Let me make it a little bigger. So you're doing something on the x. It's 3 units, shifting 3 units, but which way on the x? X is horizontal.
3 left, 4 up.
This is 3 left. And then y-axis is up and down. Positive is up. Okay? So we take each point one at a time. Go like point A, 3 left, and then 4 up. Right? So that's the notation one notation you can use to describe it. All right, so this one says sketch that triangle, and then use that transformation to move it. Okay, is that the same one we just did? Let's see.
Yes.
No, it's a little different. The translation is the same, but the actual vertices are different. All right, so A is -1, -3. That's A. B is 1, -1. That's B. And C is left 1, up and down 0. Okay, so here's our triangle. What's the transformation we're doing? Just describe it in terms of left, right, up, and down. Oh, Morgan? What does this -3 on the x mean? Okay, think of your x-axis. Which way does that go? Is it up and down or left and right? Left and right. Okay. It's a -3. So negative, which direction is the negatives on the x-axis? Yeah, so we're going left. We're going -3, left 3. How about the +4? Up 4. Okay, up 4. So that's the transformation we're doing. Okay, so take each point and then move them left 3, up 4. Okay, let's start with A. Left 3, up 4. Okay, that's A prime. Okay, take B, left 3, up 4. B prime. And take C, left 3, up 4. There's C prime. Okay, so there's our translation. Left 3, up 4. Okay, another way that you can write a translation is to use a vector. Okay? A lot of times we'll use a vector because it's a little bit shorter. And when you take trig and other courses, they also use vectors there. Okay, so basically, a vector is used to describe something that has a magnitude and a direction, which is exactly what a translation is. It has a certain amount that it's moving, and it has a certain number of units it's moving, right? Or a certain direction, sorry. Right, so you may describe a translation as move something, 3 units, and then give a direction, up. So the amount is the magnitude, 3 units. The direction in that case was up. Okay, vectors are also used in physics. Like if you want to describe the velocity of an object. So like let's say you throw a baseball. Okay, when you throw it, there's 2 things that you need to describe. How fast you threw it and which direction you threw it. And we can use a vector to do that. So when we draw a vector, like on graph paper or anywhere we draw a vector, it has an initial point, that's where it starts, and a terminal point, that's where it stops. Usually your initial point, that would be like a vertex on the pre-image, and your terminal point would be a vertex on the image. Where does it end up? Okay, so you always draw your arrow from the original picture towards the final picture. Right, so let's look at this. Okay, here's an example of a vector. Okay, there's point P. There's point P prime. What I'm going to do is just make that a little bigger so you can see the arrow, hopefully. Right, so P, P prime. Started here, and it ended up right there. Okay, that arrow is an example of a vector. And it's describing the translation. It's both things you need to know at the same time. It's describing the direction it moved in, and the length of the arrow describes how much to move it. Right? So in this case, it's 6 units right, and then 2 units up. So that's how you can figure out the left and right, because that's important to know. Just look at your point, count how many units left or right, and then how many up or down. And when we write something in vector form, we use these angle brackets, and we put the horizontal component. Okay, that's the left or right. Left would be negative, right would be positive, comma, and then the vertical component. Negative would be down, positive would be up. So doing it this way, you only need to put 2 numbers. You don't need to write x plus a number and then comma, y plus a number. That's a different way to do it. And you have to use these brackets, okay, that are pointed. What would happen if you use parentheses instead of these brackets? It wouldn't be a vector if you use parentheses. What would it be? It'd be a point, it'd be a coordinate. Okay? So if you want someone to know that you're talking about a vector, that's how you do it. So the vector we just drew above, 6 units right, 2 units up. That's how you write it. 6, comma 2, and then put the brackets on it. Okay, what would, let's just try -2, 8. Who can describe to me what that vector would do if you translated every point in a picture using that vector? All the points would do what?
Go left,
Yep, left 2
Up eight.
and up 8. Perfect. Left 2, up 8. Okay. Any questions on that? All right, so translation, pretty easy to describe it with a vector. Okay, I want to know, looking at that picture, what would be the vector that describes it? Starting at J, going to K. Need a little bigger? Yeah. Looks like we go 1, 2, 3 to the right, and then 1, 2, 3, 4 up. Always start at the end that doesn't have the arrow and go towards where the arrow is pointing. So right 3, up 4. All right, so that's the first one. How about this one? Anything, Luke?
0, 7.
Yeah, there's no left and right component here, meaning you would not be translating it left and right.
Only go up.
You're going up 7. Okay, so just up 7. Okay, and Jacob, how about that one?
Down 3.
All right, down 3. Where's that negative 3 going to go?
Where the Y would go.
Yeah, where the y would go. So make sure, even though he said it first, that's okay, but it's got to go second where the y would go. Down 3 and then
To the right 3.
to the right 3. Right is which, positive or negative? Positive. Okay. Down 3, right 3. Good. All right, so for this one, using the vector they give me up above, 4, 2, I want to translate A, B, and C using that vector. Okay, let's call the new points A prime, B prime, C prime. So if you translate A 4 units right and 2 units up, where would it be? Alyssa? Yeah, it would be at 7. So if you take 3 and you go 4 units to the right, that's 7. And if you're at -1 and you go 2 units up, it's at 1. 7, 1. Okay, how about B prime? Ariel, where would B prime be?
5, 3.
Yeah, go 4 units to the right, and then go 2 units up. Okay, and C prime, go 4 units right, be at 7, and 2 units up would be at 7. Any question on that? All right, and let's see, our last one. Looking at that, tell me the vector that I use to translate the blue picture to the red picture. And all you have to do is look at 2 corresponding points, like T and T prime.
You draw the line for us?
Draw it in?
Yeah.
Yeah. So, going this way, and then this way. So that's your vector. So in this case, it's left at how many, Ian?
-8, 2.
Yep, so -8. So left 8, up 2. And you can check if you go to R, it should also be left 8, up 2. Okay? From every point, it should be left 8, up 2. So that's how you describe a translation. All right, so the homework is on 425. Okay, I want you to try 15 to 19 all. 23 to 31, that's all. Then 39 and 40. And then skip to 44 to 49 all. And for MCAS, what did we say, 5 through 8. Okay, do the next four multiple choice.